All right, so that's, again, just scalings in all sorts of things. All right, so let's, this is for your assignment and just good general knowledge, Buckingham pi theorem, it's called, with these sort of, that's not a bad title, I guess. Yeah, dimensional equations. You often hear the term dimensional analysis, right? Just saying, well, you know, if this thing is meters squared and this one is, you know, right, then we can only put them together in certain ways. Dimensional analysis is another term. All right, so I managed to dig this up. This is, you know, I came across this as a paper to read, and I went to photocopy it because it's a long time ago. You would photocopy a lot of things. That's all you had, right? You had to photocopy, and so you eventually just you have all these books, all these journals to photocopy. You put them down, and you've got your little card. It was a whole mess, right? And just pushing it down and pressing go, and then eventually you just leave it up, and you're just like. You're like, you know, this is what graduate students should do. So it got bad. I remember once at Columbia going to photocopy a paper, and you know, it's a whole thing. It's not Googling, right? You have to pull out the thing, go to the page, and someone had torn it out. That was just such a dagger. I couldn't believe it. They'd just torn the whole paper out. At that point, I knew it was an important paper, but so bad. Okay. All right. Anyway, so it's a beautiful old paper, and of course not the first person to find it. But it's named after this character Buckingham, and the pi is just silly. We have pi. We should be just using pi for pi. It's just like it's a special one, or tau maybe, but pi. Maybe some tau fans out there, right? Tau is 2 pi. There's a movement to make that the right one. Okay. All right. So okay. So here's the idea. We've got n related quantities. We've got some system. We've got n quantities that describe it, right? So for gravity, we've got mass of the two objects and the distance between them. There's some other weird things that gravity exists, for example, but you know, you start to lay out your pieces, and somehow we hope there's an equation that combines them all, and somehow we can, you know, figure out something about our system. And so we can always sort of write this down. We could make it equal to 0, which is a bit, it may seem odd to put it to 0, but you can always just lump everything across on one side. It won't tell the story properly, but we could always do that. So here's a simple example. So this is for just a square. Area is length squared, right? It's the, and there's some notation here that I want to you know, get sorted out for you, right? So area is length squared. So our equation for this could be, right, a minus L squared equals 0. That's a weird way to express an equation for the area of a square, right? It's got length L. That's an odd thing to do, but we could do it. We could put A over L squared equals 1, right? We could do all silly things like this. Bit odd. Okay. Generally, you want to keep as much as you can, and algebra usually, you know, destroys any story, but if you want to keep the story, a physical story inside the way you lay out equations. All right, so what we want to do is, I've got one more thing to say. So these square brackets will indicate dimension. What kind of dimension is associated with this thing? And this just means, right, this just means length, right? So this is a length squared thing. It's not saying it's meters or furlongs or whatever, it's length squared. Length is, of course, just length by itself, so volume would be length cubed. Any mass, a body mass, would have just a big M associated with it. Anything that's got time would have time associated with a big T. They're our main units. There are others, but they're our main units we'll worry about. There's a footnote for us here, which is, right, dimensions, furlongs, and smoots, right? There are all sorts of funny units in the world. Let me enjoy myself for a second here. So, yes. This is a strange business. Horsepower we had. That's dimensional analysis. There's the so-called furlong-firkin fortnight system, because you could do this, right? So this furlong is 1/8 of a mile. So we actually used that on the farm I grew up with. 20 chains in a furlong. That's a cricket pitch. It's true. And then, you know, acre is 1 furlong by a chain, right? Very weird things. there's 11s in there. We talk about 12 being a great number, but there are 11s in the English metric system. So a firkin is maybe 8 gallons, I think, and a fortnight is a very good term, 14 days, fortnight. But you could, there's a madness here, right? So there's speed of light is 1.8 times 10 to the 12 furlongs per fortnight. So people have had a great time here. And then, of course, you find, right, list of humorous units of measurement. There's actually, and I think it should be in here, the smoot, right? So the smoot is, if you go to what's called the Harvard Bridge between MIT and Boston and walk across it, you'll see smoots marked out. This is like the highest level of MIT hazing, I guess. But there was a guy who turned out to be the shortest character in this incoming freshman fraternity, and they made him lay down over and over, and they measured the bridge in smoots and chalked it out, right? So it's however many smoots plus an ear or something like that. And it gets repainted. And then I think the great thing is, here it is, it's the height of, that's important, it's the height in 1958 of Oliver Smoot as measured by some idiots who later became the chairman of the American National Standards Institute. Yeah, and then the president of ISO. So he's like, I'm going to own measurement. I will get you guys back. Absolutely fantastic. There you go. He was 5'7". Yeah. So Google Earth and Google Calculator include this. You can put in, 3 feet in smoots, and it will do it for you. Okay, and then it just obviously falls apart completely into other directions. It's great, really good. Okay, so a furlong has the dimension of length, right? So does a smoot, right? So if we put brackets around a smoot, we put an L over here. So we're going to say, it's so great. We'll say, hopefully we can reassemble all of this into P, right? At most n of them, but P independent dimensionless parameters. So here's our dimensionless parameter. This is one dimensionless parameter we could write down here, right? So we could call this one, in this case, pi1 equals a over L squared, right? Or it could be pi1 equals, a cubed over length to the 6th, right? That would work too. The dimensions of pi1 equals 1, right? In the sense that there's no dimension. That's the way you write that. So if we could do that, then we have a chance of somehow figuring out what our basic equation might be made out of. And if we're really lucky, there's only one dimensionless unit, parameter. There's only one dimensionless parameter, I should say. And then we know that that's a constant, right? We can't, right? If I haven't quite made this clear, the big point is that you can't have an equation for a system that depends in any way on how you measure aspects of that system, the units, right? It doesn't matter if you use furlongs and fortnights or seconds or whatever you want to use. It can't matter. Okay, so that was our point that I just wrote on the board. F equals ma, right? So that's a weird thing to do, but this would be okay. This thing here has it's dimensionless. Of course, we don't want to write it like that because there's a little story in how this thing works here. Okay, so this is a back of the envelope situation and allows all sorts of possibilities. This is really unfortunate. This is blown out too much. This is a platypus. Let me describe the things. That's a mass of m. This is a pendulum. The platypus is the weight in this case, mass m. It's a perfect pendulum with a platypus. And we've got a length here, L, and then, of course, the gravitational field. So these are you could add other pieces, but these are the only things that really matter in here. And then there's it's swinging back and forth. It's a perfect pendulum. And there's some period, right? So there's a time unit. There's a length unit for the pendulum, the mass here, and then the gravitational field. So it's going to swing forever. So 4 quantities, as I said, length L, mass m, gravitational acceleration g, and the pendulum's period, we'll call it tau. Right? So and of course you can sort all this out, right? We get our calculus, we can do the whole thing, a little bit of physics, and we can think about how this swings, and we'll get out the actual you know, as a function of time, where this pendulum is. If we say, you know, start it at some point here and let it swing back and forth, we can do the whole dynamical piece. Right, but we want to be sneakier than that, lazy, I suppose. So let's look at these things. So there's the length of the pendulum. That has, its dimension is length. Mass, of course, is the dimension of mass. Gravity is an acceleration term, so that's distance per time squared, right? So velocity is length over time. Acceleration is length over time squared. So that's what that is. And then period is, the period of the pendulum is has a dimension t. So we have three pieces in here. There's a length scale, there's a mass scale, and a time scale. So somehow we have to combine these pieces, or, you know, it's possible we may end up with, you know, when you come to this, it's possible there could be 4 independent scales, right? We could have one that's just mass, one that's just length, one that's just time, and one that's, say, Kelvin or something, right? That will be independent. But we can see there are 3 dimensions in here and 4 unknowns, so we've got a good chance of being able to put them together. So one thing you notice straight away with this is time is here, length is here, and length is here. Mass is only here. So this, just writing this out tells you straight away there is no way that the mass of the pendulum can be in the equation that we end up with, because there's no other way we can't combine the mass of the pendulum, by which I mean this m, with any of these other variables, such to get rid of it, right? So if we're measuring this in, you know, kilograms or something, there's no other thing that has kilograms in it that can be involved in some way. Take the square root of it, you know, stack them on top of each other and eliminate the dimension of kilograms. So it can't matter. So that's a good thing to see straight away. All right, so envelope situation, we do this. So let's just sort of write down the right things. So you're going to find all possible independent combinations of what we'll now call Q1, Q2 up to Qn. So these are our parameters, and we'll call these new ones. There'll be p of them. We'll call these dimensionless quantities, right? So these are things like, this is our period of the pendulum, the mass of the pendulum, those pieces here. And these are there'll be some ratios, some things involving, you know, powers stacked together, like this thing, a over L squared, for example. And we have to figure this out. So the way to do it is to say, well, let's just make a prototype one. So we'll say, you know, there could be more than one of them. So we'll say pi sub I is going to be the first one. So again, this could be the length of the pendulum, the mass of the pendulum, the period of the pendulum. We'll raise them all to some power, and we want those powers to kind of combine so that there's no dimension of the whole thing. All right, so we want to set these powers so that we get our dimensionless quantities. And the way to do that is you can just apply this sort of dimension operator, right? Well, what's the dimension of our pi sub 1? Well, it's the dimension of Q1 to this power, right? So if this was a length, this is length, and this is 2, this is length squared. It's going to pop out the things we want, right? The dimensions of all these pieces, we need that to be 1. We need all of those powers to balance out. And it's good to go through the pendulum exercise. You know, you can, you know, it's a good basic one. I think Kepler's law is in there now as well, which is a little bit more complicated. So the dimension of Q1, right? That was our length of the pendulum. That's just going to be this capital L, right? This capital L is a very special thing. It's not a parameter. It just means the length dimension. Mass for the mass of the pendulum. Then we have the gravitational constant. So this was little g. That was length over t to the minus 2. And then we have the period. So it's t. So we can put all these pieces together. Yep. Right. So here's our little prototype one. We're going to stick it in here. The dimension is going to be length, right? Length to whatever x1 is, mass to whatever x2 is, and then this length t to the minus 2, x3, and then t to the x4. Right? This is now just sort of a way of, you know, still in a mathematical way, but these are not, right? This doesn't have a dimension. This is just saying it's a, yep. So we're going to regroup things, right? Length appears here and here. So this was the length of the pendulum, the gravitational constant, So we get a length to the x3, length to the x1. So we're going to have that. Length to the x1 plus x3. Mass is only here, as we said, by itself to the x2. And time we're going to collect from here and here. So there's going to be a minus 2x3 and a t to the x4. So these are independent objects, right? So we need this to be 0, we need this to be 0, and we need this to be 0. And that becomes our set of equations, right? x1 plus x3 has to be 0, x2 has to be 0, already solved, and then these two have to be, this sum has to be 0. So this, of course, is, what are we doing now? Yes, it's linear algebra, it's matrixology. Okay, so it's just quite delicious. So we can frame it very nicely in, yes, nutritiousness. Okay, so we can write it down like this, right? We had x1 plus x3 had to be 0, so that's what this first multiplication says. We had just x2 had to be 0 by itself, so that's what this is, right? This dot product. Just going to pick that one out. And then we had minus 2x3 plus x4, and that's what this last line says. So we had 3 equations, 4 unknowns, and our 3 equations have to be 0, 0, 0, right? And we stack them up, do the right thing, we do row reduction on this, for example. You see you don't have to do anything straight away to see that this has rank 3, right? These are independent equations. So we see some good things. It's a null space problem, right? Yes? We want matrix sends this vector to 0. So which vectors will be savaged by this matrix? This is just a little, if you're linear algebra, you need a refresh, then you should look at this again. But number of dimensionless parameters is the dimension of null space, right? So how big is your null space? And in this case, it's n, right? So this is an m by n, right? So it's a 3 by 4. It's 4 minus the rank. N is the number of columns. R is the rank. So this is 4 minus 3 in this case. So it's just to go through the linear algebra formalism, 4 and 3. So that means we just have one, right? There's only one dimensionless parameter. And that means that the upshot of that is we don't have to think about some more complicated equation. We just know that there's only one way to combine them. Then it has to be a constant. Could have some funny pieces to it, but it's a constant, basically. All right, this is the general thing of what we just did, right? So this is, just formalizing it. You don't have to worry about it too much. But it's very joyful. Null space is a spectacularly important thing. All right. Okay. And of course, this is the sort of thing, if we go back to this, yes, you can just mess around with this, right? We know x1 is minus x3. We could substitute in that. You can just do it all by hand. That's true. But for larger systems, you roll out the linear algebra and do the right thing. And we have a bigger understanding here as well, right? So we know now that it's the number of original parameters, right, minus the rank of whatever the matrix is that we construct. So you can figure this out. There are different ways to frame this, but essentially length divided by the gravitational constant times tau squared. I guess that should be in brackets, but has to be a constant. And you could have this cubed or whatever you want, right? But basically there's a length scale in here that gets canceled with the length scale here. This has 2 time scales, and this was length over time squared, so that cancels that as well. And so gravity is gravity, that's fine. And then we just have these 2 pieces sitting there and gives us this very nice observation, and again, could be just done on an envelope for sure, that the period of the pendulum is proportional to its length, which is a famous result, right? People figure this out by staring at pendulums early on, and then we're able to derive it with calculus and all sorts of things. But this is a nice little, you could just argue this. I mean, you could argue this thousands of years ago, really, if you got this dimensional piece sorted out.
I imagine there are situations where it's not obvious. The number of parameters that you need would not be obvious.
The overall one. So so it's, well, okay, well, so, yep.
Yeah, I mean, before, of course, you reduce it, you get a set of dimensionless parameters. But before that step, let's say you're just listing a set of parameters.
Yeah.
How do you, I mean, you may not know if that set is completely
Yeah, exactly.
or not.
Quite. That's so exactly right. So there's some magic in figuring out, and I'll show you some sort of profoundly shocking ones in terms of their success. Maybe you've seen these things, but there's a lot of art in that part there, a scientific kind of understanding of what will really matter. And yes, you could be missing something, which, you know, and then you figure out that that's a problem. But yeah, these are sufficiently simple systems that we can get somewhere with it.